Hey everybody. So this next little section, I'm just going to go over some standard use practices. So this is, kind of just review with a little bit of new stuff of what we just did. But I like to just bring it back and wrap it all together. So some standard use patterns of the stuff that we've been learning. All right. So first, because of the way the transforms work and how everything's centered around the origin, we typically, when we're planning to draw our object, we come up with our own object coordinate system and we draw within that. So let's draw your object in some standard object coordinate system. So for example, it's very common to make your x like this, your y up here, and 0 of course is here, and then just make it from -1 to 1, -1 to 1. Just draw your object based on 0, and then rely on your transformation matrices to put it, resize it, scale it wherever you want. So then you rely on transformations. So this is very liberating because when you come up with an object or a model, you can model it locally in your own coordinate system that makes sense for that model and not worry about where it's going to be used or how it's going to be used, because we can use transformations to fix it based on the use context. And this is exactly why you can download standardized models off the internet and use them. It doesn't matter how you're going to use it. Transformations can fix that. The other thing I want to highlight is, up until now I've mentioned the transformations in terms of a vertex, but of course, and this is probably obvious, but it's worth saying, is that you transform, when you want to transform a shape, all that you do is you transform all the vertices in a shape the same. Uniformly. So if I want to rotate an object, I just rotate all the points, and it works out really well. And some people get caught up on that and they go, really? Is that really the way it is? So I do have a couple of slides here. There we go. Yeah, let's look at these slides. So here's one. Let me just resize this so I can see what I'm doing. Here's an example. If I transform my point here this way, we've learned about that transform, but if I have a triangle, I just do all 3 points with the exact same vector and the whole triangle moves. Same thing with rotation. We learned about rotating 1 point around the origin. Well, if I rotate every point the same amount, it turns out you get a rigid rotation. The whole triangle gets rotated. The same thing goes for scale. If I take every point and I give it the same multiple, the same transformation, the whole triangle scales. So it's really that simple. If you want to transform a shape, just uniformly transform all the vertices in that shape and you'll be fine. And this was slides 3 to 5. So, and then the other thing I want to remind you of is that all of these do indeed work on the origin, and this causes no end of headaches. So I'll explain why that is again. So these all work centered on the origin. And that means that your transformation might not necessarily have the effect that you envision. So let me just draw what these look like. I'm going to draw 2 triangles here. And they're going to be the same triangle. This one's centered on the origin. And this one I'm going to put up here a little bit. It should be the same triangle. Forgive my quality there. Same triangle, okay? So then what I want to do is I'm going to rotate first. Then scale. Okay, so that's what the rotate looks like. Now this one, because it rotates from the origin, I'm going to rotate by some value. like some angle there. And I'm going to do the same in both cases. In the left case here, because it's already at the origin, you're going to get the whole triangle rotated kind of like this, because all the points rotate around the origin. In the second case, we're going to do the same rotation, but because the triangle's outside, the whole thing moves around the origin. So now we get kind of the same rotation, but instead of being centered, it's offset over here, and so it's going to kind of look like that, okay? Because the whole thing moves down. And then if I want to scale, the same thing. If I scale it up, the whole thing gets bigger in place. Over here, because it's off the origin, what's going to happen is it'll get bigger, but it'll also get further from the origin by the scale value, right? So now it's gotten B is bigger than A. Thanks, Adobe. Oh, you couldn't see that. I got an update. So, yeah, so the order of the transformation matters, and the fact that it's not around the origin can cause all kinds of headaches and problems. If you wanted to rotate this triangle, you're making an object, your triangle's up there. I want to rotate it in place. What do I do? Well, it's not hard. So instead, what we do is you first translate to the origin, then rotate, scale, or whatever you want to do, then translate back. So in this case here, what I would do was, if I have a triangle out here, oops, that's not a triangle, they grew an extra side. I have a triangle out here somewhere. The first thing you do is you calculate, all right, where's the center of my triangle? Let's find this vector there, and call that T. So I take my points, I transform it, I translate it into the center, then I do my rotation, and then I move it back. That's simple, and that's how you'd rotate it. And so you combine those, they multiply out. You're not actually moving things around, they multiply together. It'll just rotate in place. It's a really nice way to do things. All right, so the other thing that I want to remind you about is combining transformations. And I want to give you an example and talk about that just a little bit more. Remember, we can combine transformations, right? So let's say I'm going to rotate by 10 degrees. Then I want to scale by 200%. Then I want to translate to, let's say, x comma y, whatever, doesn't matter. So I'm going to call these my rotate, my scale, and my translate. I want to do those things, and we can combine them into one and pre-compute it, and the order matters, right? So if I have my point, the first thing I want to do is apply my rotation to it. And remember, it's reverse order, then my scale, then my translation, and that'll give me my new point. Now, if I have a really complicated shape with 100 points in it, of course, then you take these, you pre-compute it, you multiply them together, you pre-compute into some matrix which equals TSR, and then you just multiply that matrix times P to get your P prime. So you remember, you can do that, you can pre-compute them, you can combine them, and it's really, really quite nice. Let me go back to our slides for a second. I'll write that in slide 6. Okay. There we go. All right. So this is the next slide. So here's what it looks like. You know, here's a, you can combine transformations. And the reason I'm showing this on a slide, because I'm not going to write this out, but if I have this P and I want to multiply it by M1, M2, M3, you do it in that order. You can calculate this in the middle. And what's really cool is you get these really interesting matrices that nobody really understands. But if you start to think about it for a really long time, you might be able to figure it out. So here's my translation, which you should know by now. It's just a ty. Here's my rotation and then my scale. If I multiply those together, I get this single matrix here. Like I said, this is the part that people don't really get. Oh yeah, I scale and then I use cos, I scale and sine, and the tx's go in there. I don't know. The intuition breaks down. That's okay. But what you can see is if I multiply these out, and you can do it by hand, it's not a bad idea to practice, you get this weird matrix that will do all of those things in the order that you asked, that you did them in the first place. And if you rearrange that order, you will get a different result matrix. So that's kind of neat. All right. So what else should we remind you of? Yes, inversion. This will come up. So remember, we can invert or undo a transformation. So we can undo a transformation using the inverse, right? So if I have some matrix, I apply it to my point, I get point prime. Remember that I can do the inverse against point prime, and I'm going to get my point back, right? So matrix inverse times matrix times p is just going to be p. They cancel out. And that's really cool. Now the problem with inversion is that inversion itself, it can be slow, okay? So if you need to do it a lot, you need to pay attention to what you're doing and where you're doing it. But there are tricks for inversion, okay, to make things faster. So let's go look at slide 7. So here's an example of the kinds of tricks. So you can do the, and I'm going to come back to that in a second, but you can do the longhand way of inverting a matrix that you learned in linear algebra, but sometimes we have more information. So translate is easy. If I want to invert a translate, I just do it with the minus. I move this way or I move the opposite. I just invert the vector. If I want to rotate, again, I can undo a rotation by a negative angle. You go in the opposite direction. And for scale, if I'm going to times by s, I divide by s. And this scale is invertible as long as my scale is not 0. Right? If you scale to 0, the whole thing goes away. It's no longer affine. It's not invertible. But if it's not 0, then you can just manually come up with these inverses yourself. You don't have to do the longhand way of inverting a matrix. So keep in mind that most of the basic things you do, if you're clever, you can actually invert them pretty straightforward. Now it gets more complicated than that. Sometimes you find yourself with more complex matrices, right? Maybe you're working in a toolkit and you can get the transformation. You don't know how they got there. It just looks crazy and it's a bunch of numbers. So you can invert it a long way. So you can still do that. You can invert more complex matrices. And I shouldn't say more complex, but basically if you don't know where they came from, you can invert more complex matrices using linear algebra. Remember, not all matrices are invertible. Now, we're going to see some of those later when we learn 3D, but for now, pretty much everything we do should be invertible. Okay. Slide 8. So if I go back to my slides, so you can invert your matrix, and this is not testable, okay? But keeping in mind that this is something in your linear algebra textbook, you can use a determinant method where you come up with a bunch of these determinants, these micro pieces of the determinant, and you can calculate that, multiply by 1 over the size of A, and you can get the inverse. I haven't done this in years. You're not going to bother doing this, but it's very cool to know that you can do it if you find yourself in a situation where you need it. You can go, okay, it's slow, it's a lot of multiplication, it's a lot of work, but I can go look that up, and it's doable, and it's not crazy. It's just a bunch of math that you can copy out a formula, okay? But this is not something we'll be testing you on. This is not something we'll be testing you on in this course. So the point is to know that you can do it, not to memorize how to do it, okay? Now the last thing I want to remind of is that transformations as a change of basis. And this is really cool. And I'm going to keep coming back to this because bases are such a really cool concept. That's really, once you get it, you're like, that's really simple. Like, it shouldn't be that simple, but it is. So remember, if I have a basis, and this is in 2D, right? I have my vertices here. I'm going to draw this out actually. Here's my coordinate system, and I'm going to draw a basis in here, something like this. This is my x. Let's call it u, and this is my v, which is like my y. Remember that these are orthogonal. That's what you want them to be. So in this case, this is my vx, vy. This is my u. I should actually be consistent. Okay, ux, uy. This is my vx, vy, and then homogeneous coordinates. And keeping in mind I have my origin here, now we can see, look, I can just put my translation in there. I can just do that, and it works out just right. So here's a basis function that'll take any point in this blue space, right? And if I multiply that here, this is p, I'll get this point in real space, okay, in my global system. So I can use that, and then we've talked about how to invert that. But I wanted to show this on a slide because this is actually pretty neat. How cleanly this works out. Okay. So here's an example, very similar to my slide. We have an object, a point in here, I and j are u and v, my global coordinate system, and over here u and v is my local basis. I have to transform the object, okay? So I have this transformation. I rotate by 15 degrees, then I scale by half, then I translate by 3, 2. And if you do that, you do the rotation matrix, you do the scale, you translate, you multiply it out, you do all the math, it actually gives you this little matrix here, which of course doesn't really mean much to you. It's just a bunch of numbers, but you apply this matrix to your point, and it'll convert it from there to the other point system. So this is my u based on my slide. This is my v, and look, translation at x and translation in y. So you can actually get this. This is the coordinates of my u, and this is the coordinates of my v, and this is my translation. So this is my basis function, and the origin is right there. So for any point, px and py, I can translate it from this local space into my global coordinate system by just multiplying it by this basis and adding the offset. Now I showed you this because we didn't construct this manually in terms of a basis. We just applied these transformations and looked at the result. And the result breaks down nicely, just like I told you it would. These are my u and my v vectors, and this is my translation x and my translation y for this basis function. So that's kind of neat to see. All right, go back to my slides. Cool. So that's all I'm really going to talk about with this little catch-up section and example section. That's all I really wanted to go over. Just some ideas of how we're using these transformations. In the next section, we'll jump right into how to the transformation pipeline and how we go from our object all the way to the raster.